Okay, YouTube, in this last video graphing secant and cosecant functions, just want to run through one more example of graphing a cosecant function by basically graphing its reciprocal, the sine function. And in this video, I just want to explore what this would look like maybe if we had some translation here. We can see that it seems that we're going to have some horizontal translation here, as well as deal with some fraction units, some rational units. And so let's go ahead and take a look at this graph here. It says, first of all, identify the amplitude, period, and starting point for the graph, but then also construct our frame and graph just one cycle of this function. So again, when you graph reciprocal functions like this, the tact or the method will be to just go ahead and graph its reciprocal itself, since we're so good at graphing these, and then we'll just use the characteristics that we recognize from the original function here in order to get our reciprocal function. So here we have this. We're going to go ahead and record the values of a, b, c, and d within our function, and then go ahead and construct our frame. So our a value here is a half. We have a b value also of a half. I'm going to try to squeeze that in there. Our c value, now remember c is backwards, so we have a positive pi, and our d value, it doesn't seem that we have a d value. I'll even explicitly fill this in here. And so to graph this, I suppose we need three things. We need its amplitude, and that would just be the absolute value of our a value here. So the absolute value of a half, of course, is just a half. And so we say the period. We need the length of the frame. We have the height of the frame with the amplitude. We need the length of the frame. So the period is 2 pi over b, with respect to sine and cosine and their reciprocals. So 2 pi over b, and our b value is a half. Now the interesting thing is, of course, when you divide by a fraction, we got to multiply with the reciprocal. So we're going to say 2 pi times 2 over 1, which of course would just be double this. So we say 4 pi. I'm going to put a box for this. This is the length of our frame. And then we just need the starting point. Remember, we did actually translate in this particular example. So we have c over b. So we have c as our pi value here over b, and this b value is a half. And then comma d. At least we have a, d is 0. So we're going to say pi divided by a half, same thing as pi times 2. So we get 2 pi, comma, 0. And so when we start this graph here, I'm going to go ahead and get my axes set up here. I'll even extend this a little bit further, north and south. Taking a look at this, we're going to say our starting point then is c over b comma d. And so our starting point is at 2 pi comma 0. Let's just pick an arbitrary x value to call 2 pi. We're going to say that this is 2 pi right here. Why not? And then also comma 0. We would say that this is the starting point of our frame then. And so let's go above and below how far we need to. Now the a value of a half means that at least the sine curve would have an amplitude of a half. So if that's the case, I'm going to call this way up here 1 and way down here -1. And so that way we can get away with kind of saying that this would be the halfway mark in between. And so our frame would extend, oops, I almost went along the y-axis there. Our frame would extend upward and downward from like this x value right here. Now, in terms of how far out would it go, remember that the length of our frame is 4 pi in length, and we're starting at 2 pi. So if we were to go out, 4 pi in length from here, which is our period length. I suppose we would say that we have 2 pi plus 4 pi. We have 2 pi plus 4 pi. Sorry to write this out because, of course, we should all know that this is 6 pi. This would be the ending point. So I say 6 pi would be reasonably, like maybe in this neighborhood right here. And so with this frame now, we can go ahead and partition this here. We're just going to drop in our sine curve. So we'll cut this in half. We got to label this the average of 2 pi and 4 pi, or 6 pi is 4 pi. We have 4 pi. We'll split these in half. That's 5 pi. You guessed it. This one's 3 pi. And so our sine curve with a positive a value without being reflected would start at a 0, go to its maximum, go back to a 0, go to its minimum, and then go back to a 0 again. And so we'd say here's our reciprocal sine curve. So now the question really is, truly, what would our cosecant curve look like? So we'll get out this kind of reddish tone here. And we know we would have asymptotes wherever this original function had zeros, or if it's translated upward or downward, it doesn't have to be an actual 0 of that translated function. It just has to be a 0 with respect to the frame, kind of on the midline there. So that being said, we have asymptotes here and here, and we would say then, I know that our graph proceeds through this crest and through this trough and makes these swoops here. Okay, so we get this here and this here. And so with respect to, let's talk about a few things here. Amplitude, we have no amplitude. Remember this graph? There is no halfway distance between its maximum and minimum, because since it proceeds upward and downwards indefinitely, alternatingly, we can see that it has no max and no min, so no halfway point between those. The period of this graph looks like the period would be the same as the period of the sine curve that its reciprocal is. So we would say the period is 4 pi, and this was the same thing we just got 2 pi over b over here with, or got with 2 pi over b. And then the starting point, we saw the starting point was 2 pi comma 0. Wonderful news, it's still 2 pi comma 0 on the reciprocal function. So I suppose the only difference is that we have no amplitude. When we talk about these three values here, we just have no amplitude when it comes to reciprocal functions. Cheers.